How sad. I am 7 minutes late in recording, and we missed a lot of things that I just talked about. Let me just really quickly go back if it's okay. I'm going to be really brief though. You can go back onto this document. Basically, your essay should be a work in progress. Elder Holland said it best. He said, "Be ye therefore perfect eventually." And then he repeated Elder Nelson by saying, "Here mortality perfection is still pending." So that means that our papers can be that same way. We can just keep working on them back and forth and learning things from them. I also noticed in the essays there's a lot of passive voice, which is not a very strong way to say what you want to say. Learn how to speak in active voice. And you'll have to look that up because I don't have a lot of time to teach you that. Or we can talk about it next week as well. One thing I did notice in almost every one of your papers, because we're used to writing talks for church, and in talks for church, we use a lot of first person, second person words, which is I, you, us, our, your, we, etc. All of those. My. And it's okay to speak that way when you're speaking to people. But in formal writing, you don't want to do that because it does something to the reader and they just want to stop reading because they feel like you're assuming that you know what they're thinking because you're saying the word you or you're saying the word I, and they really don't want to learn about what you feel. They want to learn about what can be felt. That was passive voice, by the way. They want to learn what can be felt. When we speak, we can speak in passive voice if we want to. But you want to use words that are going to be direct, but not using first and second person. And what I did was I put down some websites here. And these 3 websites, and you can go onto them. This one too. See, if you click on that, you can see this little website. You go on there and study it in your own time because I think it's going to help you a lot, and we don't have a lot of time to talk about it. I'm interested in you and your brains and what you want to say, and I want to help you be able to use elocution to be able to persuade your reader. And these websites will help you, and you can take time to read them when you can. And remember how to get to this. It's on the collaborations in your Canvas. All right, are we ready? Do you have any questions before we go? Any questions before we go on? Okay, because I want to get right into Galileo. And what I want to do is I want to I've got to find my Galileo on my Kindle here. Here it is. Okay. There. Is that showing Galileo? One interesting thing I want to tell all of you. Well, no, let me ask you first. Stop sharing for a minute. What did you think of Galileo? You, Kendall, that's funny. Not Kimberly, Madeline.
I really liked it. I thought it was really cool because I don't know, because like I'll move. Me when I was younger, then I was in elementary school, and so like public school and stuff. So you'd learn about people like this, except you never really got to. When I was younger, I thought that heavier ball would be dropped faster. This is talking about the first part of Galileo that you read. But then I think my mom or someone told me, no, they're actually the same. And I was like, really? Like, okay. And I never really totally got around to the logic of it. So it was really cool to come back here and be able to see it.
You're bringing up a point that is going to be, this is passive voice as well. You're bringing up a point that is going to be a life changer. And what that means is you are building upon, every year you're building upon things that you kind of learned before, but you're getting deeper and broader and deeper and broader as we go. So even when parents speak to their little 3-year-old about really complex things, they're not going to get 1% of it, but they're going to get a little bit. And as they're continually working together as parent and child and student and mentor, and they're getting in their books, and they're going to be building upon that. And it's quite amazing, because that's what changes our lives, is to continually expose ourselves to the best. And as we expose ourselves, even if we get 10%, we are building upon what we knew before. That's a really good point. I'm really glad that you had that experience. Anything else? I think Kendall, I think you had your hand raised. You still do.
Yeah, I did. Oh, okay. So I love astronomy, and like I've been really excited to learn about Galileo. I was struggling a little bit with it though, because it was kind of like doing Euclid for me, and like especially yesterday, doing this like model was a little bit difficult, but I thought it was cool that I could relate that to. He related it to Archimedes, and like that was his kind of thing, and so it was cool to see Archimedes and Galileo and Euclid, and kind of to make all those connections. So I like it better now.
Oh, good. And you brought up another point, is that Galileo always stood upon the shoulders of the giants of his day. He stood on Aristotle's shoulders, and then Archimedes, and was learning and developing, and and Euclid. So that's what we are going to be doing our whole lives as well. Good. And another thing that Kendall did not say is she struggled with this, but she called her cousin, and they worked together. And then they called me in, and I think we were on for about an hour to hour and a half. I don't know how long.
We were both almost in tears. It was pretty bad.
She was almost in tears. So whenever you get to that point, will you call me? Because I it was so funny, because I had other things to do. I was supposed to be doing papers, correcting papers, but I was so excited to get into Galileo with you, that you and Edie and I learned so much just by coming together. And I'm willing to sacrifice other things to do that when you need that help. If you want to.
Something that helped me was like, and I thought, oh gosh, I'm the only one who's struggling with this. Like, I'm so done. Like, what? And so I called Edie, and she's like, Kendall, I don't get it. And so it was so comforting to have like someone else and be able to go talk to my teacher. So I'm going to go talk to her.
And by raise of hands, who else struggled?
Reading Galileo?
Yeah, reading Galileo. Okay, so even Lanny raised her hand for a second there. So that's exactly what is going to happen. I read one of the Humanities papers this morning that the author of the paper said, we grow through struggles, and that's the truth. I never learned how to pray so much in my life as when I opened up Plato and Galileo and Aristotle. But now, because I've exposed myself with this principle that Madeline was talking about, I'm building upon knowledge that I've gained, and it's getting a little easier. So anyway, thank you for contacting me. I hope everyone will contact me, or that I hope you find study groups. I hope that you get together. I know one study group has been going on since the very beginning, and I'm proud of them. They get together on Zoom, and they study, and they are understanding things better. So keep it going. Madeline.
I just wanted to say something else. I really enjoyed reading Galileo, and one of the things, I don't know, I had it so close. You might have to come back to me because I forgot what it was.
Okay.
Oh, no, okay, now I remember.
Okay.
Did any of you, right at the first part, did any of you, while I was reading his argument on why falling bodies move at the same rate, even if they're different weights, then it was so interesting to see his logic with, what's that name, Simplicio? How Simplicio and, I forget his name.
Segredo.
Segredo, is that the main guy? I thought that was the middle guy.
That's the middle guy. So Salviati.
Yeah, Salviati and Simplicio. Then when they were kind of going on and off, then it was so interesting to see Galileo's logic, and he just did like such a good job of saying like, I don't know. Okay, let's do this. You pick a number. Okay, let's do this. You pick this number, so this would be this, right? Am I right? Yes. How would Aristotle say this? Like he really had them get in the discussion, so then when he showed them that they were wrong, they were like, I don't know, it was more possible for them to like see that they were wrong. And I don't know if that would help them be happy about that. They'd probably still be pretty mad. But it was interesting how he really, I loved his logic. It was so awesome.
You're bringing up another really good point, Madeline, that in dialogue, and we just talked about it, and Kendall just wrote about the dialogue in the chat box. When people can dialogue together, that is when they learn the best. But you have to have something to dialogue about, right? So you have to do the reading. Then you've got questions, you've got concerns, you're not understanding. So whether you're Simplicio or Segredo, you go to that Salviati, the smartest of the group, and you start asking questions, even if the questions feel dumb, just like Simplicio did. And that's so key to learning. Okay. But I'm so happy. Yes, Madeline is muffled for me too. No, for me too. But I could understand a little bit. I don't know why, Madeline. Maybe it's because you're not close enough to your mic, but I still could hear you a little. And I think I'm hearing what you said, that you enjoyed it and that you loved the dialogue. Incidentally, before we get to Kendall, her hand's raised, Galileo was a student of humanities. He studied everything, and he was also a poet. Poets usually really recognize this idea of dialogue and of action in like Shakespeare has this action because of the dialogue that he creates. This action, you're seeing people what's the word I'm looking for? You're seeing the people work with each other, move in circles sometimes, not understanding each other, but moving backwards and forwards. And there's a lot of action in the dialogue. And he understood that. And he incidentally lived in the time of Shakespeare as well. I don't know if they knew each other. He was down in Italy and Shakespeare was up in England, but they lived at the same time. There was this boom of drama. And he was using that idea of drama in his dialogues. So it was good. Kendall.
Like you were saying, the best way to learn is through dialogue. I love when you said that, because yesterday I actually thought I was getting it, but like I told Eliana, I came up with my own philosophy. Like I was like, oh, this is how it goes, and I'm like making my own model, and it was not that at all. It was so like comforting to talk with Edie and be like, yeah, this is not like, that's not correct. And so we were able to talk through it with you and be able to understand it. And I think even just relating that to the gospel, like thinking that we have it but not really, and then going and praying about it or whatever can help.
Good. Another problem that we had was I was a little dorky with my question Tuesday. I haven't looked at the question yet today, but it was my fault. Earbuds, yes. I think part of this is I've got a little flaw in my life right now, and that's I've taken on a lot with teaching you, and I not only teach you, but I do other classes as well. I have to get the recordings up on Canvas. I've got to do all these papers, correct them and get them back to you. And it's just a lot I've got on my plate. But I will tell you, I am invigorated when I work with you. I'm invigorated when I'm looking at your papers. I'm invigorated when I'm reading Galileo, preparing for this. But sometimes I mess up by writing dorky questions. But I imagine some of you were mature and went along with it and tried to figure out how to answer that anyway. But I want you to know it's not your fault if you were feeling uncomfortable with some of the questions. Not your fault. You're going to do the very best you can, and I'm going to take all of that into consideration. And I think Lanny will too, as she's helping me a lot of extra time making comments on your papers, and I really appreciate that. Okay, I want to get into the real meat, and I want to read with you. And I've got it on Kindle. The only problem that I don't have is I wish that we could read and have the picture sitting next to us. And maybe what we can do is I may ask some questions right now that all of you can discuss right now while I'm trying to find how to copy a picture and get it up so that I can show both things. So what question can I ask? I may want to ask Edie and Kendall to moderate a discussion on equilibrium. Could you do that since we spent an hour and a half together with it? So maybe you can kind of explain what page that picture is on, and everybody can go to that page while I'm trying to get that picture up, and then we'll continue it, okay? So the time is for you, and Edie and Kendall start to moderate that discussion.
And how long are we doing this?
Just until I
have
can.
to leave early.
You have to do what?
I have to leave early.
Oh, not more than 3, 4, or 5 minutes. I just have to copy a picture.
Okay.
I wanted to do this before class, but I was busy with extra questions after the writing class. So.
Okay, so it's on page 317. If everyone, it's so much easier to go there and look at it, or else like to see the measurements and go there instead of explaining.
Yeah, so Kendall and I, when we were trying to discover this, we thought it had to do something, and you guys, it was ridiculous, but we thought it had something to do with light, because there's like a reference in Kendall.
Because of the word fracture. And
yeah, fracture.
I went to light and I was like, oh.
But it wasn't until we saw this little...
the ginormous title at like the top of the page?
Yeah. So this diagram, it was only when we saw this that we started to actually understand it. So I don't know, where do you want to start?
Ask them questions, what they understand. Ask them what they understand.
Then
you get them talking more.
Yeah, that's true. What did you guys learn from this? Or were there things that were confusing about equilibrium?
Sorry, which page is it? I was grabbing my book.
317.
317.
Okay.
Well, it starts before that. I mean, it really starts in page 315, but the picture right here, the diagram is right there.
I'm almost done.
Did anyone have like any, as we were reading yesterday, did anything connect, or did you just have like any aha moments, or was it all kind of like muffled for me? For me, it was all muffled until we talked about it.
That's a good question. Answer, everybody, because I think it's good to express some of your weaknesses as well as some of the strengths. What did you think? What'd you feel? I'm back because I'm sharing.
When I was reading it, I realized that it's very similar to like Euclid or any of the like even philosophers, or not only philosophers, but like the scientists and mathematicians of that day. They explained everything word by word. So they didn't have like equations. It was having to go through the process to understand it completely. So I had to like stop and look back at the picture and see how it applied.
Excellent example, Edie. Does anybody know who moved us forward from, just put this down here, moved us forward from words to explain things, from words to explain things to equations? Does anybody know? Kendall.
Isaac Newton.
What?
Isaac Newton.
Yes. I heard you say, I was looking at Edie, and I thought, oh, what does that have to do with it? I just didn't hear very well. Isaac Newton. Everyone, I want you to see, this is my little Kindle. Do you see how he's using this line HI, which shows HI? So it's this little beam here, this balance beam, but he's calling it HI because those are the names of the ends of the beam. So it's HI, it's balance beam HI, just like what it says right here. And then he's talking about the prism, which is the beam below. He calls it a prism because it's got sides to it. I believe that's why. Now, it's very hard to see these letters here and here and here and here, but you can imagine that they're there. You can look at your book. But he's talking about the prism AB, and that is because he's referring to this end as A and this end as B, and so it's prism AB. So he's using words to describe things, and not for 100 years will we ever see equations, which are going to look like algebraic equations, and that's Isaac Newton who gives us that. And it makes it a little different to do math with words than it is with equations, with what you're used to doing in Saxon math or whatever it is. We call that kind of math Newtonian math because it deals with equations. And we call this kind of math Euclidean math or Galilean math, but it's normally called Euclidean math because it's all done in words, which is very different for us. We're not used to it. So I want to go forward, and I want to read this all together, and I want maybe everybody to take a turn. I don't know how to call on you, so I just want you just kind of raise your hand when we come to a next paragraph. But let's start with Segredo here. And by the way, when you see E in Italian, and it should be right here after this period, it's A as in egg, okay? It's not Segredo. But when you see I in Salviati, the I is the E sound. Just a little language there. So Segredo, can somebody read? Well, no, I wanted to start back here. Okay, right here, Salviati, I believe this is Salviati, yes. He is explaining what they've just been talking about. They've been talking about these long beams. See this balance beam here? Imagine that in steel or in glass. And they're talking about pulling it with its horizontal resistance, meaning one side's being pulled, the other side's being pulled like this way. And how much more stronger it is that way than if somebody fixes that pull into a wall. So it's fixed here and it's coming out, and you break it. you don't have to put as much power or much strength behind that to bend it as you do to pull it enough to break it. It's exponentially I'm speaking in Spanish, exponentially more strong to pull it this way than to break it this way. Okay, and that's what they're talking about. Joseph, you have your hand raised.
Yeah, I was just wanting to read some when we're ready.
Oh, perfect. You can be the first one.
Okay.
You could do the first two. Oops, with Kindle, it just kind of changes pages without you really even wanting to. So let's start. I'm going to have you maybe read Simplicio and Salviati right here. So Salviati's just finished explaining that difference of force that I just talked about, that there's different ideas, or there's different ways, there's different strengths in material, and the strength depends on which way you're going to try to exert that force. Okay? All right, go ahead, Joseph.
Can you say this?
Simplicio. Mm-hmm.
Simplicio. This was demonstrated first of all by Aristotle in Questions of Method. Salviati. Yes, I am willing to concede in priority in point of time, but as regards rigor of demonstration,
Right here, the first place.
Okay, the first place must be given to Archimedes on a single proposition proved in his book on the equilibrium of planes, and not only on the explanation of the lever, but also those of most mechanical devices.
Okay, I'm going to stop you there. So the lever we know of in a few more pages, it's going to show a picture of the lever where there's this rock, which is the resistance, D, and you've got the lever, which is the beam that's got its foot underneath the rock, and it's got a fulcrum that it's resting on. And the fulcrum, it's going to talk about how if the fulcrum's closer to the point of resistance, then it's easy, then you have less power that you have to push onto the end of that lever. If the fulcrum is further away from that resistance, the rock, then you have to put so much more pressure on that point. I hope you can see me in this little picture in my little video. I hope this is all showing, because I don't see myself here. I just see some of you. But you put so much more pressure on that when the fulcrum is further away from the rock. That's what he's going to be talking about a little bit later. So he is saying, now going back, what is he saying about Archimedes with this, what Joseph just read?
He's saying Archimedes already proved it. Archimedes is the one who was like, give me a lever and I can move the whole world. Was that Archimedes?
You were muddled at part of it.
Oh, sorry. Was Archimedes the one who said, if you give me a lever, I will move the whole world? If you give me a place to stand on.
Oh, you got me. Look it up and let me know. I totally remember that,
yes,
but I don't.
Archimedes.
Okay, thank you so much, Jace. Thanks. So yes, Archimedes already tried some of this, but he did it in a single proposition. But let's see what he's going to continue on saying about Archimedes. So next person, read Segredo. Jenna.
Now, since the principle is fundamental to all the demonstrations which you propose to set forth, would it not be advisable to give us a complete and thorough proof of this proposition, unless possibly it would take too much time?
Okay, Salviati, who would like to read? Jace. And I'll turn the page when it's time.
Yes, that would be quite proper, but it is better that. Why is my? I'm gonna mute it. So it's fine. Okay, I'm gonna have to do it. But it's better, I think, to approach our subject in a manner somewhat different from that employed by Archimedes.
You stop
That is,
there. So he's now going to go on something different, right? He's going to go on beyond what Archimedes said. Okay, go ahead. Right here.
That is, I shall assume merely that which equals weights placed in a balance of equal arms will produce equilibrium, a principle also assumed by Archimedes, and then prove two things: that it is no less true that unequal weights will produce equilibrium when the arms of the steelyard have lengths inversely proportional to the weight suspended from them, and that it amounts to the same thing whether one places equal weights at equal distances or unequal weights at distances that bear to each other the inverse ratio of their weights.
Okay, what is he saying, Jace? Oh, what did I just do? He's going to prove two things, okay? What is he going to prove? Someone?
He's saying the length of your pole has to be inversely proportional to the weight that you have on it, which is something that we've been, like, inverse proportions is something we talk about in our chemistry class.
Mm-hmm. So now I want you to remember that word, those two words, because it's going to make a lot, it's going to be the full solution or resolution to equilibrium, okay? This is his math without an equation, but it will become an equation someday, 100 years hence, right? So think of inverse, where's the word? Inverse proportions, okay? And we're gonna go forward. Jace, will you continue reading? And I don't know where my little thing is to change the page, but I'll try to do my best.
Can I ask something real quick?
Sure.
Are inverse proportions just assume as like reciprocal fractions? Is that what he means?
I heard some of your words.
Oh, darn it. I'll just put it in the chat box.
Okay, I know you were asking a question about inverse something. Okay, Eliana, it is really disturbing when you're trying to talk and everything you say echoes. Yeah, I don't have an echo on my end. Is everybody else having an echo when they talk? Is it because...
Madeline and Jace both.
Okay, do you hear an... You girls are echoes. Are you hearing an echo from me?
No, I don't hear an echo from you. I hear an echo from myself now, though.
Okay, what I'm going to do is I'm going to turn my volume down, and I'm going to try these. I had them on in the writing class, but earbuds really do help with echo if they work. But this wasn't going to let me hear anybody, so let me try this again. Okay, can you hear me? Okay, somebody talk so I can see if I can hear them.
I can hear you, and I'm not echoing anymore.
Okay, can you hear me?
Talk to me.
Hello?
Okay, I don't hear anything, so I'm going to have to take them off. But Edie, close your door. Maybe that helps. Oh, okay. Well, we're going to have to do it that way. Sorry about... Okay, Madeline said, are inverse proportions the same as reciprocals? One. I don't think they are the same. Inverse proportions would be, and we're going to get to this, Madeline, we're going to see See this length from here to this line, and this line to this line? Okay, look up here from this line to this line and this line to this line. Those are inverse, showing this is the shorter area and this is the longer area. This is the short area inverse, in inverse proportion, and over here. That's kind of where we're going to get to. It may be reciprocals. I'm not very good with math. Oh, good, Madeline. See if that works. A lot of times it does, especially if you've got two people in the same household that are using the computer for the same class. Okay, Jace, I want you to continue. Oh, Kendall, do you have a question?
Well, what I was saying about Euclid earlier, at the bottom of this page, it says it's taken from, this notion comes from Euclid Elements, Book 5, Definition 17, Proposition 22. So I just thought it was cool that it was Euclid.
That is so cool. Yes. Okay, good. Was this where we were? Where were we? Is it greater? Yes, okay. Had you finished this and now we're ready to go here, Jace? Is that right? Or maybe we should have somebody else read. Let's try somebody else if that's okay, Jace. Get everybody have a chance. Who would like to raise their hand and read? Lucy, you're raising your hand the other way. So I'll have you read. How's that?
Do I start in order?
Yes.
In order to make this matter clear, imagine a prism or solid cylinder AB suspended at each end of the rod HI and supported by two threads HA and IB.
Stop there. Stop there. Okay, so let's do that. And I know many of you tried to do this in homework yesterday, but I want to still do this in all together. So where is solid cylinder or prism AB? Just blurt it out. Let's be fast.
It's the cube that's at the bottom, whatever it is.
Yes. So we've got AB. So this is our solid cylinder. So we're imagining this. Actually, we get to see it. Now we see it suspended at each end of the rod HI. Where's the rod HI?
It's just the rod on top.
Yeah, HI. Good. And supported by two threads, HA and IB. Where are those?
There.
What's that?
Like the strings on the end.
On the ends. Okay, HA and IB. Don't imagine these lines yet, these strings, okay? So he's imagining that is what we're looking at. Now keep going, and I may stop you again, Lucy.
It is evident that if I attach a thread C at the middle point of the...
Right here. So here's the string attached here, and it's going to go up and connect to a tree or something. Okay. At the middle point of the
balance beam HI, the entire prism AB will, according to the principle assumed, hang in equilibrium, since one half its weight lies on one side and the other half on the other side of the point of suspension C. Now
okay.
suppose...
Let me stop there. Is everybody following that so far? Tell me if you're not. Just raise your hand digitally if you're not following so far, and we'll go back to where you're not understanding. Okay, I think everybody's all right. So let's keep going. Oh, by the way, when you see a number like this just means a reference point to where you're going to find his original, this is where his original writing is. For instance, he wrote in Latin and Italian, and in his original work, and I'm not sure if it's in Latin or Italian, but it's in one of those, you will go to number 153, and that will tell you that you're right here, okay? So it doesn't mean anything for us unless you want to go back and learn that language and get into his own words. But that's what that means. Okay, keep going, Lucy.
Now suppose the prism to be divided into unequal parts by a plane through the line D.
Stop.
And let the
So here's the line D, and yes, Madeline, equilibrium just means balanced, okay? Here's the line D, and then we're going to imagine cutting this right here, okay? We're dividing this. Okay, keep going right here.
And let the part DA be the larger and DB the smaller. This division having been made, imagine a thread ED attached at the point E and supporting the parts AD and DB in order that these parts may remain in the same position relative to line HI.
Okay, stop there. Does everybody follow that now? We've got the line ED now that has been added, and at the point E right here, and supporting the parts AD, which is AD, this part of the prism, okay? And also DB, okay? Keep going. Right here.
And then the relative position of the prism and the beam HI remains unchanged. There can be no doubt that the prism will maintain its former state of equilibrium, but circumstances would remain the same if that part of the prism which is now held up at the ends by the threads AH and DE were supported at the middle by a single thread GL. And likewise.
Okay, so now we've got this here, right? What else did he talk about? Held up at the ends by the threads AH right here and DE right here were supported at the middle. So he's saying now this prism, this area of the prism is being held up by ED and GL and AH, okay? I think we're right here now. And why don't we have Elizabeth chime in right here?
And likewise, the other part, DB, would not change position if held by a thread FM placed at its middle point.
Right here. Right here. Okay.
Suppose now the threads HA, ED, and IB to be removed, leaving only the two GL and FN.
Stop right there. Okay. Do you see what just now happened? What are we doing now? Eliana?
You're removing all of these thread supports besides GL and FM.
Right. So we've just got those two. Okay, go ahead. I think we're right here. Elizabeth, why don't you keep going?
Then the same equilibrium will be maintained so long as the suspension is at C. Now let us consider that we have here two heavy bodies, AD and DB, hung at the ends of G and F of a balance being G and F in equilibrium about the point C, so that the line GC is the distance from C to the point of suspension of the heavy body AD, while CF is the distance at which the other.
And I'm not going to turn the page yet. So he's saying the distance between, let's see, well, and I'm going to have you guys explain. What is she just now saying? And I know she didn't really finish, but let's get to this before we change the page. Now let's consider we have two heavy bodies, AD and DB. Okay, they're two heavy bodies. And they're hung where? They're hung by G and F. G and F. Okay, now what are we going to be doing? Do you see it says, so that the line CG, and the line just means this line between C and G, right there. Do you see that? Kind of look at the measurement here in your eyes. Just kind of see it's kind of short. The line CG is the distance from C to the point of suspension of the heavy body AD. So it's kind of the shorter part, and this is kind of the longer part. While CF, look at this, this is CF, that's the longer part, is the distance at which the other, and this is going to take us here. Yikes. It's not turning. I have a feeling it's going to turn a couple of pages and did it? Yeah. DB is supported. Yeah. So this in relation to this, Madeline, remember when we were talking about inverse proportions? This in relation to this log, this big one, and this relation, C to F, and this. What are you seeing there?
Wouldn't it be more G to E, A to D, E to F, D to B?
Nope, he's
where it splits.
He's talking about where you're suspending it. G to C and C to F. Do you see that there's a balance there?
Mm-hmm.
And then you look down.
And that's the same as those flipped over. That's awesome.
It's flipped, so it's inverse. So A to D is balanced, where this thread is closer to the suspension, whereas this other big heavy body here is balanced with a thread that's further away from this suspension. Because the further away you get from the fulcrum, this is not really a fulcrum, but if you can see that, the further away, no, that's wrong. I'm wrong here. Forget what I said. I was just trying to see something and make a suggestion, but I'm wrong. But you can see that the smaller body is suspended by further away from the line of suspension because it doesn't need as much strength. Okay, this one needs more strength, so it needs to come closer to the line of suspension. Make sense? Kind of? Eliana.
I was just going to say something funny because this entire time I've been looking at it, I've actually not seen it as the wood hanging. I've seen it as the wood with maybe metal barbs coming out and holding up this rod. And so when you started talking about it hanging, I saw it for the first time and I was like, oh my gosh, it is hanging. Something's wrong with my brain. But the funny thing is because it is inverse proportionality, it's pretty much the same principle if you look at it either way.
Yes. Yes. So interesting. Somebody in this class wrote their article or their essay on the great power that came from looking at the picture of the Pieta while reading the description of the Pieta, while pondering in their mind about the whole thing, and how much better it gave their perception. I'm thinking of that right now. Sometimes if we add a discussion along with looking at a picture, along with reading a description, it gives us better perception and another testimony of why we need to get together and discuss things with each other. We only meet once a week. If I were to have you meet with me 2 or 3 or 4 times a week, it would be astronomically expensive. As it is, I already spend hundreds of hours every month, lots of hours doing all the corrections, getting all the assignments on. I'm spending a lot of time. There's not even time for me to meet with you every week. I would like to, but try to get with each other. Try to get with each other as much as you can to discuss this. It's fun. Thank you, Eliana. That's interesting. Perception is so interesting. Okay. He's now going to continue talking about these inverse proportions. All the remainder of this time that he's talking about these lines, EI. And I want the next person to read, I want them to read as slowly as possible so that people can go from the words to the picture, or you can just look at the picture while the next person is reading and see if you can see these inverse proportions. Where were we? Was it right here, Elizabeth, that you ended?
I think it's at the beginning.
Right up here?
Yeah.
Oh, okay. Who would like to read next? Raise your hand. Brinley, would you like to read?
Sure.
Okay. So read as slowly as possible. I mean, not really boringly slow.
So,
Right here.
okay. It remains, that's what I read?
Yep.
It remains now only to show that these distances bear to each other the inverse ratio of the weights themselves. That is, the distance GC is to the distance CF, as the prism DB is to the prism DA. A proposition which we shall prove as follows. Since the line GE is half of EH and EF is half of EI, the whole length
Go a little bit slower.
The whole length GF will be half of the entire line HI, and therefore equal to CI. If now we subtract the common part CF, the remainder GC will be equal to the remainder FI. That is to FE. And if to each of these we add CE, we shall have GE equal to CF. Hence, GE is to EF, as FC is to CG. But GE and EF bear the same ratio to each other as do their doubles, HE and EI. That is the same ratio as the prism AD to DB.
Okay. Did everybody get that? Did you see some inverse ratios there? Dylan is you're saying, oh, you saw some inverse ratios, Dylan?
I saw ratios, but I didn't understand the whole thing.
Okay, and she was, I know you were trying to read slow, but sometimes we need to even read slower. I want everyone to look at this picture again. I want to read that again. I want you to see it because it's fascinating. It lets you see things that you may not have even saw before. So let me go back to where she started. Okay, it remains now only to show that these distances bear to each other the inverse ratio of the weights themselves. That is, the distance GC, look at that, the distance GC is to the distance CF. Okay, the distance GC to the distance CF, we're talking about ratios here, as the prism DB is to the prism DA. You see that? There's the short GC is to BD as CF is to AD. You see that? Everybody? What about you, Dylan? See that? Okay, good. So then, where am I? A proposition which we shall prove as follows. Now here's where he's going to prove it. Since the line GE, this is the line GE, G to E, is half of EH, see that? And EF is half of EI, the whole length GF will be half of the entire line HI. So GF is half of the line HI. And the whole length GF, oh, I just said that. will be half of the entire line HI, and therefore equal to CI, which is half as well. So GF is equal to CI. Now, do you see that? In length, okay? Now, if we subtract the common part, CF, so let's just subtract this whole from the whole beam measurement. We subtract this common part, CF, the remainder GC will be equal to the remainder FI, that is to FE. That one is a hard one for me. And if to each of these we add CE, so we're going to add to both of those that we just did. Now, we kind of got to do this on paper. If we add CE,
maybe you can use the highlighter on your screen.
Yeah, it's kind of hard. Okay, then I'd have to kind of go over it again.
You don't have to do the whole thing. It's fine.
Okay, let me move this up. This little thing needs to go up. Okay. So let's see, if we subtract the common part CF, I'm not sure how to do that. So we're going to subtract this. I lost where I was. CF, the remainder GC will be equal to the remainder FI. Okay, so this remainder here, if we subtracted this, this remainder is equal to this. Okay, now we see that. That works better, Eliana. Thank you. That is to FE. That's also the same. And if to each of these we add CE, so if we add CE to both of these, so we're going to add this to both of these, which I can't really do here, we shall have GE. So if I add this to this to this, I'm going to have GE. If I add this amount to this one, I'm going to have G to E. Okay. We shall have GE equal to CF, which is also, well, that's the same thing. GE is equal to CF. Hence, GE is to EF as FC is to CG. And we just kind of did that. So now, is that helping you follow? Dylan, what do you think?
Yeah.
It seems like it's like, why are we doing this? But this is really the beginnings of, getting into this idea of how proportions and how ratios are super important to equilibrium and to strength. Okay. I want to go forward, and I know we haven't touched a lot on this. We haven't finished to the end, but I really wanted to get to, falling bodies. Did anybody take advantage of some of the videos? Oh, Eliana, you've got your hand raised. Was that from before?
Oh, I didn't mean to raise my hand.
Oh, okay. Did anybody watch any of the videos at the beginning of the overview, the lesson overview for this week? Raise your hand if you did. I think only Lanny.
Are you referring to the videos that were like on the help? I don't know. Didn't we watch a video? Is that one of the videos that are included?
Yeah, I showed one to you and Kendall yesterday.
And you showed one to me the day before, I think.
Oh, possibly.
Yes.
Yeah. Okay. Sometimes it's really important to go on Google and find some videos. And I wanted to show you, let me share my screen, because I want to get to this idea of falling bodies and discuss it. And I hope that Are you studying it today and tomorrow? Falling bodies? Got to look at that.
I studied it on Monday, I think.
A little bit, yeah.
Oh, is there more?
Mostly on Monday was reading about the ships, the small ships and the big ships. Does anybody know the difference of what the problem with big ships is? What is the problem with bigger things? Kendall.
So on this day, I kind of struggled too, and so I had to ask my dad. He came and showed me, and he put like 2 cups here, and he put one long skewer right here, and like put our finger, and it totally just broke. And so then we cut it like into smaller pieces and moved the cups closer and laid it across, and we tried to like break it, and it didn't break. And then that was only 1, so adding like 10, which he says, add 10, you really can't break it. And so like relating that to the ships, like the big ones, or like what the lever one, then he put it into the wall and it's like sticking out this far, then you can just break like that. But if it's farther in, and it's like going to be harder to break.
Yes, or even different sizes and thicknesses will have a yes, Edie.
It needs more structure. It relies on things that isn't, it relies on more than just on its own.
What is it?
The boat. So the boat relies on other structures to help keep it together and to make it float, I guess.
The small one or the big one?
The bigger one. So if one of those structures breaks, which is like more likely to break, you have a greater consequence of having it like sink.
Okay, so you're right. The bigger ship, the proportion, and he's talking about proportions here, the proportion of volume increases for a bigger ship. It just increases. But what's interesting is that the area does not increase as fast. And this is what Galileo invented, or he discovered. Sorry. As the volume increases, the area does not increase as fast, and so it becomes weak. And the pressure from the water will cave in. The weight of the boat and the pressure of the water will break the big ship unless it has a bunch of scaffolding and supports inside its what is this called, the boat? Is it the bow? I can't remember what parts of the boats are. There must be much more thick supports in there. I have an example of this. I have 2 spoons. One is a dessert spoon, which some of my children always set the table when we're serving soup. They serve it with a dessert spoon and we don't get enough in our mouth. We need to teach them that we need a soup spoon. So I've got a dessert spoon and a soup spoon. And this is longer than this one. But I want you to notice, and I hope it shows, I hope you can see can you see which one is thicker? So which one's thicker? Okay, cute, Lucy and Elizabeth. I feel like I'm with, is it the 2 kings in Alice in Wonderland that always do the same thing? I can't remember what it is, but you guys are reminding me of that. So which one's thicker?
The bigger one.
Yeah, it has to be, because when you lengthen it, this becomes weak. The skinnier part becomes weak. And I could probably easily do this. Well, I'm not doing it because it's strong enough. On this, because it's shorter, it doesn't need to be as thick. And I'm hoping that all of you will go and look at everything now and try to see this idea that the bigger things have to have more support than the smaller things. I hope you notice that. I hope you notice that when you've got a bigger book. See this paperback book, this little tiny paperback book, when I open up the pages, this back stays good. It doesn't really break. But if I've got this, I'm not going to break this, but this is a little bit bigger book. This is a book that is called The Two New Sciences that I read in college. You have excerpts of it in the book that you bought. But in a bigger book, if I'm going to do this, it is much easier for this back to break because it's bigger. It expanded in volume, but the area didn't expand enough to strengthen it, and it's going to need a lot more support there for me to be able to open it up and read it without it breaking. You're going to see this in everything. Let's go and look at a video. Okay.
I have a quick question before we do that. So can I share the screen to a whiteboard so I can draw it really quick? I think that will make the most sense.
Yeah.
Okay. Did that work?
Yeah.
Okay.
It does.
So you showed us two books, and so one of them was like, I'm just drawing the book like it's open, and here's the spine, and then like all the pages are coming out like that. And so pretend that's the smaller book. So let's say, I don't know, this is 4x, the length is, and then this little right here is like x. Let's say, I don't know. So for the bigger book, then you're saying that it's more like 8x right here, and then are you saying that this is still only x? So you're saying that, and that's, so they need to make it 2x, so they really should have it right there, and then it would be the same?
It would be, if it's stronger, then you're not going to have anything break. But bookmakers don't give you thicker here unless you get a hardback. And so almost does anybody own a paperback in Les Miserables? And what has happened to the spine? Okay, I guess it's obvious what's happened to the spine. It just breaks because the bigger you are, the weaker it is. Very good, Madeline.
So, but I was confused because when I was reading Galileo in here, then he was saying, it was almost like he was saying, for like his bone picture, did any of you guys read that? So it's on page, what?
I don't have the book with me.
Where is it? Oh, okay. So on page, I'm gonna not be able to find it, but what he does is he draws a picture like of a bone, and then he draws a picture of a bone that, oh, right here, it's on page 332. I don't know if we're reading this, but I guess maybe we are, maybe we're not. But it says, to illustrate briefly, I have sketched a bone whose natural length has been increased 3 times, and whose thickness has been multiplied until for a correspondingly large animal, it would perform the same function which the small bone performs for its small animal. From the figures here shown, you can see how out of proportion the enlarged bone it appears. Clearly then, if one wishes to maintain in a great giant the same proportion of limb as that found in an ordinary man, one must either find a harder and stronger material for making the bones, or one must admit a diminution of strength in comparison with men of medium stature. And he goes on. But what he's saying, I'm confused because with the book thing that you just showed us, then the proportions are directly related. So maybe the length is exactly 3 times bigger than the width, let's say. But in here he's saying if you wanted it to perform the same function, you'd have to have like the length maybe 6 times bigger, but the width would be more than 2. It'd be like something else. So he's almost going like against proportions. Does anyone have any ideas on this? I was really confused.
Who's saying it? Who is the one that's?
Oh,
who is the one that's saying this?
Salviati.
Salviati. Okay, so that is Galileo himself speaking that. It may be a different proportion. What I was saying, what you suggested, was not even what Galileo said. So we can't use the exact equation of what you're thinking. But what his whole premise in this day 1 and day 2 is that size, the larger the thing, the longer the thing, the more strength it has to withstand the power of resistance. It has to be stronger. And sometimes he uses proportions, sometimes he does. I'm not a real mathematician.
Sorry to be like so like crazy about this, but I actually have one more thing too, and then I'll be done. But this is just a really interesting question. I don't want to throw it out there. So he talks about how like bigger things need to have more support or whatever. What if the atoms? Like when building a ship, then it's not necessarily that the trees that you use it are bigger. It's that you need more wood. So I think it's almost a not perfect example of what he means, because what if the trees actually were bigger, like the atoms in the trees were like 10 times bigger than the normal atoms? You know what I mean? What if every single thing was bigger even up to the very last bit? Because then it would have so much of the same proportions that I wonder if it would be able to withstand it. I guess you might have to like change the gravity of the earth too. What do you guys think? Sorry.
Good question.
Does anyone have anything?
Wait, so you are like saying that the trees aren't going to be bigger, but you're using more wood to make the bigger one stronger?
No, I'm saying that to make a bigger ship, or to make a longer ship, you're not going to have a bigger plank of wood. You're going to have 2 planks of wood that are the same size as the 1 plank in the small ship. So I don't think it's the best example, because it isn't really bigger, it's just more stuff. Does that make sense?
Oh, yeah, okay.
Lanny had a suggestion for you, Madeline. She said that it helps to read the replies from Simplicio and Salviati, and probably Segredo, of how they reply to him.
Okay.
And so I wish we had more time to go into that, because I think that would be good. I really wanted to show you some of these videos so that we could discuss. But I think these are great. And you know what, Madeline? You look like a great candidate to start a weekly or even a daily study group where you can gather some of your friends together and read and discuss these, because I think that's how you're going to learn the very best. I wish we could meet every day this week. I kind of had that in my mind a couple weeks ago, but then I realized I can't do that. There you go. Look at what Lanny said. And you seem to get it and grasp it quite well, so you would be a great tutor. There you go. Why don't you join a study group? Okay, I am going to share my screen. I want to show this. I want to show 2, but I think we may only have time for 1. Oh, I forgot to share my computer sound. Share computer sound right there. Oops. I'm really having a senior moment. Okay, this is 5 minutes. This is the law of falling bodies.
What do you think is stronger, an ant or an elephant? An elephant can lift more weight than an ant, but what about their strength compared to their body size? The answer might surprise you. An elephant can lift 500 kilograms, which is 10% of its body weight. An ant can only lift 1/millionth as much, but that amount is actually 50 times its body weight. Ants use their impressive strength to move food and materials to their colonies. How much can you lift? The average person, between the size of an ant and an elephant, can only lift about half of his own weight. Why is an ant so strong?
First, we need to understand a principle called the square-cube law, which Galileo came up with over 400 years ago. He observed that when an object grows in size, its volume increases faster than its area. Let's picture a cube. The area of one face on the cube is the length squared, and the volume is the length cubed, hence the square-cube law. This cube has sides that are 1 centimeter long. The area of a face on the cube is 1 square centimeter, and its volume is 1 cubic centimeter. Now this cube has sides that are twice as long. The area of its face is 4 square centimeters, but the volume is now 8 cubic centimeters. Doubling the length of the sides quadruples the area, but octuples the volume. As the object gets bigger, the ratio between its area and volume changes. There are important consequences when an object's volume grows faster than its area, because it changes the way it could interact with its surroundings.
The effects of the square-cube law can be observed in our everyday life. For example, in designing buildings. We can make small-scale models of buildings out of papier-mâché, but real houses are made of wood, brick, and metal. But why can't we just build a real house out of papier-mâché? The amount of weight that a structure can support is relative to the cross-sectional area, but the building's own weight is proportional to volume. Since the square-cube law told us that volume increases faster than area, a bigger building will weigh more but might not have enough area to support its own weight. These two towers are made of the same materials, but only the small one can support its own weight. Because of this, engineers need to use stronger materials like bricks to design real buildings that have larger dimensions. For a similar reason, an ant can carry more relative to its body weight than an elephant. And this is also the reason why monster ants do not exist. Strength is proportional to the cross-sectional area of their legs, while weight is proportional to their volume. Here you see a small ant holding its weight. If we now scale up the ant, we see that the ant's legs can no longer support its weight and it collapses. And hey look, the small ant can even bring treats back to its friends.
The square-cube law is also observed in aerodynamics, which is the science of flying and falling. You may have learned that gravity causes matter to fall towards the ground, and that gravity makes objects of any mass fall at the same speed. Why is it then that in real life some objects seem to fall faster than others? A falling object actually experiences two forces, gravity and air resistance, which is also called drag. Gravity makes the object fall faster while drag slows it down. The force from gravity is proportional to the volume of an object, while drag is proportional to its exposed area. Remember again that when things get bigger, volume increases faster than area. If we drop these two different sized helicopters from 4 stories high, what happens?
I'm going to stop this for a minute because I think it needs to get caught up. It's really struggling. Let's see if it's going
to... What happens? As predicted, the bigger helicopter fell faster because the drag, which goes with area, increases more slowly than weight, which goes with volume.
Let's review what we've learned today.
Whoops.
The square-cube law tells us that when an object grows in size, its volume increases faster than its area. We've seen how this can be applied to buildings, animals, and falling objects. Look around you. What else can you explain with the square-cube law?
Okay, sorry about that little problem. There's also, in the course modules, we don't have a lot of time, but I want to show you where you can get some other videos that I collected a couple weeks ago and put on here. So if you go down to week 9, where we are, whoops, that was week 19. Here. So if you go to the overview, I really hope that you watch. This one is what we just watched, but the link was bad, so I looked it up somewhere else. I'm going to have to go fix that. But this one right here, Galileo Falling Bodies, is excellent. It's PBS. It's excellent. And it shows why Galileo proved, or how Galileo proved Aristotle wrong. So hopefully you'll go there and look at that up. We could go on and on. And I feel so badly for Madeline. She probably has so much to say, and we spend a lot of time reading. I want to talk with you more, Madeline. It looks like Eliana does too. So anyone who wants to stay after class, go take a little break and eat some food and then come back, you're welcome to do that. Thank you for coming. Thank you for experiencing him, and we're still going to keep reading him Thursday and Friday. So continue getting into him and doing what we did today. I showed you an experience of how you can look at the picture, read the explanation, and see what he's looking at.
Thank you.
Okay. Thank you. Have a wonderful week. Oh, and next week, by the way, sorry, next week, we are going to be watching the Roman Roads lectures and getting into Shakespeare. So make sure that you've purchased the Roman Roads lectures. Your parents should know about that from an email. And you'll be watching lecture 1 and lecture 2, Monday and Tuesday. And I hope to have questions up there for you to look for and to answer. I'm going to try and catch up this week with that. And I promised everybody that I would have study questions out by now for the written final. I haven't done that yet. I will. So just keep studying, keep working, keep learning, and you'll do fine. Okay, anything else? Any questions? Great. Have a good day. I'll stop recording now.